Hello, everyone. Welcome to another spooky session of LeetCode Live, coming to you stronger than ever from LeetCode. And it's the first day of October. Time has flown. We started our journey back in the middle of July, and now we're here in the beginning of October, sitting at 304 questions with a nice sort of, starting to do a little bit of easies, getting a little bit of mediums in there. We're making progress. Before you know it, we might even start doing some hards. We've come a long way. And before we start, I actually want to talk about some quick things. So, as you all know, I maintain a YouTube channel called LeetCode Live. By the way, I hope you all enjoy, hopefully some of you are festive and you all enjoy the little bit of festivities that I'm introducing into the channel. I am a huge festive person. I grew up that way. And so I'm hoping that this little spooky JavaScript and medium like LeetCode will bring some fun for everyone. But one thing I did yesterday that I'm really proud of, that I want to sort of direct everyone's attention to is, and some of you may already know this, I recently started a podcast called Castware. So that's sort of like podcast and software. And it's been going great. And yesterday I released another episode with a competitive programmer that goes by the name of Ivan. And he was referred to me by someone on my Discord server, and we had a phenomenal conversation. Ivan's a really, really cool guy. He definitely is very passionate about coding. He loves competitive programming, and he even does tutoring for those that are looking to get some more tailored help. So if you're into doing some podcasts, if you like listening to podcasts, you want to hear about people and their LeetCode experiences, definitely check this podcast out. Head over to the Castware channel and take a listen. It's even available on Spotify if that's your thing, under the same name, Castware. So back to LeetCode, back to the thing we are all here for. I didn't do an episode yesterday because I was doing Castware. We're very close to the 500 subscriber mark. Once I get that community feature unlocked, I'll be able to relay this information to you all. But without further ado, let's go ahead and get started. We're going to continue today with doing some more medium questions because today's Saturday, and the new deal was Tuesdays, Thursdays, and Saturdays we're going to do medium questions. So I think we did pretty good last time. Let's see the first question we have on our plate today. Hopefully it's not too bad, and if it is, that's fine. We'll think about it on the stream. We'll give ourselves maybe 20-30 minutes, and if not, we'll go to another one. We can always come back to this one during one of our weekly roundup sessions. All right, so you have an array R of length n, where R of I equals 2 times I, plus 1 for all valid values of I. In other words, 0 is less than or equal to I, which is less than n. In one operation, you can select two indices, x and y, where 0 is less than x, y is less than n, and subtract 1 from R of x and add 1 to R of y. In other words, perform R of x minus equals 1 and R of y plus or equals 1. The goal is to make all the elements of the array equal. It is guaranteed that all the elements of the array can be made equal using sum operations. Given an integer n, the length of the array, return the minimum number of operations needed to make all the elements of array equal. So let's see, here we have 1, 3, and 5. Okay, first operation, x equals 2 and y equals 0. This leads to 2, 3, 4. In the second operation, choose x equals 2 and y equals 0. Again, r is 1 or 3, 3. Now, what is the, you have an array of length n where r of I, 2 times I plus 1 for all valid values. So it's always going to be 1, 3, 5. Okay, I see. So I think like maybe just going off the top right here, maybe the best thing to do is like how many operations would it take to make all the numbers equal 3, for example, right? Because at the end, that's what we end up with. This is 2, and this becomes 4, and that's one operation, then 3 and 3. What if we had one of 6, right? So let's say we had 1, 3, 5, 7, 9, and 11. I guess that's what we're getting at here. So I almost feel like, well, let me see. This is like, should we try to make all the numbers the middle of this one? For example, 1, 3, 5, and 7. This is what? This is an even length array. So maybe if we take the middle two and we just pick the number in between them, which is 6, what if we tried to make all of them 6? What would that look like? And what if we just started from the ends? And this is what I mean, right? So make this 2, make this 10. Okay, that's one operation. Make this 3, make this 9. That's another operation. Make this 4, make this 8. That's another operation. Make this 5, make this 7. That's another operation. Make this 6, make this 6. That's another operation. Make this 4, make this 8. That's another operation. Make this 5, make this 7. That's another operation. Let's see, make this 6, make this 6. That's another operation. And finally, we make this one 6 and this one 6, and that gives us 9. So I almost think that, and I feel like I've seen this question before, but we just pick the one in the middle. We pick the one in the middle because it almost kind of makes sense to me that, like, actually, let me check something real quick. Just bear with me. You know that I'm always doing this here. Okay, I just wanted to like check to make sure the audio was working. So it makes sense to me since everything is like the number in the middle is equidistant to like the larger number and the smallest number, right? The distance between the biggest number and the smallest number is the same. So I feel like trying to make all the numbers the same as the middle one would be the shortest distance, because trying to make everything the same as 1 would require more steps from 5, right? It would take 2 on 3, and then it would take another 4 on 5, right, to get to 1. But if we made everything the same as 3, it would take, well, what would it be if we made everything to 1? It would be 2 and 4, that's 1, and then 1 and 3, and then what? Just 2 and then 1, that's 4, right? So why don't we try to figure out the number? And actually, is there also like a faster way to do it? I think once we figure that out, all we need to do, I think once we figure out that the answer is 6, or rather, once we figure out that the number we want to change it to is 6, could we just actually take the difference of both? Like, how far is, let's see, it's 5 away from the first one. From this one, it's 3. And then from this one, it's 1. Right? The distance from 1 to 6 is 5. And then we go in here. The distance from 3 to 6 is 3. So that's 5 plus 3 is 8. I've never actually thought of it that way, but that might just be the answer right there. That could be the answer, and we might not even need to build the array up. Because one thing I was thinking is, you know, we have this array right here that I drew out that makes it a little bit easier to sort of like reason about. But we can also just create two numbers, 1 and then 11. And let me see. You're given an array of length n where r of I equals 2 times I plus 1 for all values of I. If n is 6, let's see, 2 times for I less than n. So I just do 2 times 5 plus 1. That's 11, and that'd be the last one. 2 times let's see, 2 times 2 plus 1, that will give me 5. Okay, so let's say number 1, let's say let low is equal to 1, and let high equals 2 times n, or 2 times n minus 1. 2 times n minus 1, and can we just do 2 times n minus 1 plus 1? We can also do 2 times n minus 1. 2 times n minus 1. And I don't even need this, right? Because order of operations will dictate that the multiplication happens first, 2 times n, and then minus 1, so we'll get high. So I think what I can do, let's see, and now I'm looking for the midpoint of these two, right? If I add 1 plus 5, that will give me, 1 plus 5 is 6 divided by 2, that's the midpoint. In the other one, when we had what? 1, 3, 5, 7, 9, 11. If I do 1 plus 11 divided by 2, that's 6, which is the midpoint here. So I think what we can do, let min operations equals 0. Let's say let mid equal math.floor of low plus high, right? Because 2 times n is 6. Yep, 2 times low plus high divided by 2. That will give me mid. And let me just go over that one more time. Our low would be 1. Our high would be 2 times n, which is 3, so that's 2 times n is 6 minus 1 is 5. Our midpoint will be low plus high, which is 1 plus 5, 6 divided by 2. That's 3. Okay, now, what is it that we want to do? I think what we can say is while low is less than or equal to high, we can say min operations plus or equals math.abs, the distance from either of these, right? Mid minus low, let's say. And then we can do low plus or equals 2 and high minus equals 2. I think we can do this, right? So what do we get for this last one here? This is 6, right? 1, 3, 5, 7, 9, 11. So let's see, low starts at 1, high starts at 11. While low is less than high, it is. Min operations plus or equals math.abs of mid, which is 6 minus low, that's 5. So let's say min currently equals 5. And then we do low plus or equals 2 and high minus equals 2. Low is still less than or equal to high. So now we calculate 6 minus 3, which is 3, and we add that. Now we go plus or equals 2, minus equals 2. Low is still less than high. Distance between 6 minus 5 is 1, so we add 1 to 9. Plus or equals 2, minus equals 2. Now low is greater than 9, so we exit. Similarly here, let's do this one. Low and high. The midpoint here is 3. So we do min operations is mid, which is 3 minus low, that's 2. We add 1 here, or we add 2 rather, and then we add another 2 here. Distance is 0, so we don't add anything to the output, and we still get 2. So I think that can be the answer. And then here we just say return min operations. I think this could be it. Let's check it out. All right. And let's do all the example test cases. Or I don't even know if that's what I did the first time. 2 and 9, 2 and 9. Feeling good about this, so let's go ahead and submit and see what happens. Nice. Yeah, very cool. This was a really cool question, and complete transparency, like I tried this question before a long time ago, and I did the whole thing with the array, and I had like multiple loops, so I honestly, I don't even know what happened tonight. It might just be like a good night tonight. But this is very nice, right? Because the space complexity here is constant. Now, the time complexity, is it really, what is it really? Like, how many operations am I doing here? How many times do I go through this loop? Is it just n divided by 2? I guess it won't be n divided by 2 because that would be 1. How many times did we go through it from 1 through 11? We increased 1 to 3, that's once. 3 to 5, that's twice. 5 to 7, that's 3 times. And that's already bigger. So it might just be half, right? Like half the size of the array, right? Because we're just ever going to the midpoint. So it could be n divided by 2. I feel really good about this one. One-liner mathematical solution. This is crazy here. Return. Whoa. Okay. This is different. Very simple mathematical solution. In the middle of the array. Triangular sequence. Okay. I want to see one that's like close to what we solved though. n minus 1 divided by 2. That's the thing, but now everyone is going to start. So okay, so here's my hot take on LeetCode questions, because like I guess like one thing that I don't really like that much is it could very well be the case that all of these people genuinely came up with this answer on their own, but my hot take is someone here came up with the answer. Let's say this person, Archit91. I don't know if they're okay, so it looks like they're proposing a similar answer, sort of. Let's say this person was the first person to come up with the best answer. But then, oh, okay, I see. Both of this person's answers are at the top. But like, let's say this person was the best one, and then S. Gallivan came and then just kind of copied this answer and changed it up a little bit and maybe just got a little luckier and got more hits. But all these are sort of the same. And let me see. MMD, what's up? What's up, my dude? Hope you're enjoying the slight festive spin I took on today's stream. I don't know if you can see the title or if you can see the thumbnail, or if you were even able to see, once the stream goes up, you'll see the transition I used, if you will. Tried to make it a little more festive since it's October and we're entering into Halloween. Well, it makes me feel good that I know that when I tried to do this question probably a year ago, I did not do it as well as I did now. But now it's also making me feel not so great that it looks like there's an even better way of doing it, a mathematical way. The sum of linearly increasing numbers is the very definition of a triangular number, which in this case doubled because the numbers are 2 apart. The standard formula for our triangular number is n times n plus 1 divided by 2. All right. If n is even, there's all this stuff. Rounding error if n is odd. If you think the array has points forming on a line or a graph, you can think of that line as a diagonal of a box of area of n times 2 of n. Yeah, these mathy questions I think are cool, but sometimes when a solution leans too heavily on math, I'm not as, I don't know how practical that can be, because the reality is probably a lot of people don't use math too heavily during software or when they're doing normal software engineering. And I say normal more in the case of like, your full stack web development or just full stack development in general. The person that I spoke to yesterday on the podcast, for example, he's more into like quantitative analysis. So something like this might be more beneficial to them. But let's just say that I'm okay saying that probably most people are not going into a field like that. So all this to say that I'm really happy with the solution I came up with, and it's worlds better than anything I ever thought of even a couple months ago. So that's good progress. I'll add this to my list because I do like this question a lot. All right, so starting off strong. So let's see this one. Okay, like this one for sure I was never able to solve, but let's see if our practice has taught us anything. All right, so given an array of integers pre-order, which represents the pre-order traversal of a BST, construct the tree and return its root. It is guaranteed that there is always possible to find a binary search tree with the given requirements for the given test cases. A binary search tree is a binary tree. All right, cool. I'm going to have a little bit drink of water. If you all have water, if you haven't drank water, drink some water. Let's take a little water break. Okay, so How can we solve this? So pre-order means that we're going to process the node first before we ever visit any of its children. So 8, 5, 1, 7, 10, 12. How can we go about doing this? I really, really want to try and solve this, because if I can solve this, I will really, really feel good. And we have time. We got 40 minutes. I normally do these streams for an hour, so got 40 minutes to tackle this one. Even if we only do this one for this stream, I'll be really happy. How can we try to think about this one? We're given this pre-order array, and we want to return this. So if I'm printing this out, right, I'll do 8, 5, 1, 7. Then I'll come here and do 10 and 12. But we just never know. Oh, and also, okay, I see. Also, like, because it's pre-order, and I don't even know if this is like the right line of thinking. This is just what I'm thinking now. But then again, remember, this is what my stream is for, right? You're hearing my raw thoughts, even if I'm approaching it incorrectly. You're hearing me speak about it, and you're understanding how I'm trying to approach this. Like, it's a binary search tree, so like if this is, I know the first thing I print is going to be my root in this case, because it's pre-order. If it wasn't pre-order, if it was even in order or post-order, then I might have to think about this differently. But because it's pre-order, I know that this 8 is going to be the first thing, like the root of this tree. And then I get to the next one, and this one's less than 8, so I can make it 8 left child. Then I get to this one, which is less than 5, so it can be the left of 5. Then I get to 7, which is greater than 5, so I'll make it the right child of 5. But then now, okay, we get to 10, that's greater than 8. So somehow I have to like remember this one. Now, do we need to remember it? There might be some other data structures we can use. I don't know why, but I feel like a stack maybe could help me. I mean, a stack is, like as we're doing recursion, especially with like tree traversal, we're just using a stack like implicitly, right? Like the execution stack, the execution record stack frames, if you will. So if I were to use a stack with this, and let me just put this here so we can see it. So like I put an 8. Oh wait, too far. So I put an 8. Okay, that's cool. Now I say, well, 5 is less than 8. So I make it maybe I can just make it the child of, maybe I can make it the left child of 8. Okay. And then, okay, and then I see though a 1. Maybe that can be the left of 5. Okay, and then I see a 7. Now, 7 is greater than 1. So maybe that means I like, maybe not. I was going to do something like, oh, 7 is greater than 1, and it's greater than 5. But then, like, if it's greater than 1, and I don't do anything with the 1, why would I stop and do something with the 5? Is that because I see that it's not also greater than the 8? So something that we got to think about here. BST from pre-order traversal. I mean, I could certainly keep appending to the left, but left. When I get to the next biggest one, 8517, we get to the next biggest one, and what do we do from here? Can a stack help? Maybe not. I don't want to get too fixated on that. The idea of a stack here. I wonder if we can also like maybe like what if like I found the first, like, okay, I have an 8 and I find the next smallest thing, but I also find the next greatest thing. So it's like 8 to the left is 5, to the right is 10. And like, what if what if I like broke this up into smaller subarrays where I had something like this? And what would this mean here? Then I have 8, 5, 7. Or actually, why not say that we have an 8 up here, and then we have a 5, 1, 7, and then a 10. Now at the 5, right? Like let's say we have something like this. And then maybe here I can say, well, I want to find the next smallest thing, which is the 5. Okay. And then I want to find the next largest thing, which is a 10. Then here we're just left with 1, 7, and here we're left with 12, which naturally just becomes this. And then from the 1, there is no next smaller one, so that can just be left as 1. But then there is a next greater one, which is the 7. Maybe something like this could work, but the the process of like, okay, finding, it'd be nice if we said like find the bounds, or like where does the next greater thing start? I'm also wondering if, because pre-order would do 8, 5, 1, 7, 10, 12. If I started from the back, would that change anything? Could that make it better? Maybe I should also think about, maybe it'd be beneficial for us to actually draw out, if we were to draw out the tree, or not the tree, but more like, well, yeah, the tree. Draw out the tree, or maybe just like the stack, and see how it's actually built up. If I had something like this, like we're gonna pop the 8, and then we're gonna pop, or rather push the 8, we're gonna push the 5, we're gonna push the 1, we're gonna print the 1, so we'll pop this, then we'll push 7, we'll pop that, we'll pop the 5, then an 8, we'll go and push 10 and 12. It's almost like I'm trying to see how the stack can work here. Pre-order traversal. Construct the tree and return. It is guaranteed that there's always possible to find a binary search tree with the given requirements for the given test cases. I guess I could do something where I try and find, like, in my recursive call, I can do a slice where my root is just the thing at this array, and then I find the index of the largest thing, or the first smallest one, and then the first largest one. So I'm thinking maybe we can do something like this, like, okay, beginning of array is root, find first smallest, find first largest, and then rinse and repeat. Maybe we can do that. So what if we did, let's see, const pre-root, we're going to set equal to new tree node of pre-order at 0. Now I want to see something. MDN find index. Well, there's find index that takes in a callback element greater than 13. See also find method, which returns the first element that satisfies the testing function. Well, I need the index. That's the thing. I need the index of both of those. Okay, this is what I'm going to try and do. Okay, apologies for this. What if I did first smallest is pre-order dot find index of element, and here we'll say, I'm just going to call this E. E is less than, let's see, pre-order of 0. And then here we'll say first largest equals pre-order find index of E, where E is larger than pre-order of 0. Then what I kind of want to do is say pre-root.left is equal to BST from pre-order, where I'm actually going to slice it from the index of first smallest up onto first largest. And then here pre-root.right is equal to BST from pre-order of pre-order.slice starting from the first largest, return pre-root. That's kind of what I'm thinking so far, and let's kind of go through this and see how this looks, right? Let's just start from the beginning again. So we have pre-root here is the first thing in this array. So here I'm going to say 8 is the first one. Now I'm going to find the index of the first smallest one that is less than 8, right? In this case, it's 5. So I'll say 5 has an index of 1. The first largest is 10, 0, 1, 2, 3, 4, which has an index of 4. Now to the left, I'm going to pass in the subarray that starts from the first smallest, 1, and goes up to the first largest. Slice includes everything up to but not including the last index. So here we'll send in the array 5, 1, 7. And then similarly, we'll say 10 and 12. All right. All right, we'll just send exactly 10 and 12, 10 all the way to the end. Now I want to see what happens if I do find index. What does this say here? If no element satisfies the testing function, -1 is returned. If I try to do, let's see, if I try to slice, if I have like 1, 2, 3 dot slice -1. Okay, so -1 is actually going to return a 3. So what I want to do if I don't find something, if we don't find something, that can be the base case. And the left in that case will just be, yeah, so first smallest, find index. Let's see, pre-root.left, here I guess we can set it equal to like first smallest is equal to -1. If it is equal to -1, then we can maybe just say null. Let's do that instead. Else we'll just call it for the next one. Similarly to this, we'll say first largest equals -1. Here we can say null or BST from pre-order, and then we'll just return pre-order, or rather return pre-root. This is what I'm thinking. Not entirely sure, but I think it's a good first effort try, and I'm very excited to try it out. Let me go ahead and put this down here. Let's run this guy. Let's see what we get. Okay, so I mean, like, I'm extremely happy for even getting this output. I swear, I promise you all that this never, I never made it this far. I never made it this far previously. Like, as we're getting deeper and deeper into LeetCode, I'm telling you without a doubt, I've never made it this far in my LeetCode journey, to the point where I feel like I'm really getting these questions. It's really being beneficial. I can see it. But before I start talking too much, Let's see what the next test case gives us. So 1 null 3, so looks good on both. So let's go ahead and submit this and let's see what we get. 4 and 0. Okay, we get 4 and 2 and then 4 and 0. So I'm very curious about this. First of all, where did this 0 come from? Okay. 4 and 2. Why would it have been 4 and 2? Okay, so we make, so the pre-root is 4. The first smallest is at index 1. Okay, and the first largest should just be null. Right, expected 4 and 2. Now, why do some of these have, see, some of these actually want you to return null, but in this case, it doesn't even want you to put a null there. 4 and 2, but there'd at least be one null, right? Maybe it's just not showing it here, but let's see if we can figure out where that 0 is coming from. So I make pre-root that, then I have first smallest, which should be index 1, first largest, preorder.find index, where e is greater than preorder of 0, which is 4. And it's strictly greater, so there's nothing. That should be -1. So pre-root.left, if first smallest equals -1, which is not, then I'll just call it with 2, 0. So let's say, or rather 2, right, to first largest. Oh, wait a second, 2, -1. I guess in this case, we have to do, let's think about this. It might be because of this, right? Because if first largest is -1, how are we going to, what is it that we want to do here? I only want to get a slice of this smallest if first largest was actually found. If it's -1, what can we do here? I think there's a better way for us to do this here. Instead of relying on a test case like this, let's see. The -1, that really makes it a little bit annoying. Slice from first smallest to first largest. If there is no first largest, we should just get the remainder of the array. I mean, what we could do, because what would happen here? If first smallest is -1, because there's actually two cases, right? What if there's nothing that's smaller? If there's nothing that's smaller, then maybe, let's see. Yeah, let's think about the smallest case. If first smallest is equal to -1, that means there is nothing smaller, so we just set it equal to null. Okay, now if there's no largest one, if first largest is equal to -1, we can just set that to null, but then we also need to change this. So I feel like maybe I can make this let here if first largest equals -1. Maybe we just set first largest equals to preorder.length. So it just takes the length of the remainder of the array. That way this won't fail. I think that might work. But if not, let's just, we can try it out anyway. Let's run this. Ooh, okay, it didn't like that. And I wish I knew for what test case that messed up. Was it also this one? Okay, so it also messes up with that one. So first largest equals pre-order dot length. Is there a case here where we can actually wrap? If I do 1, 2, 3 dot slice of 1 to -1, that's going to give me 2. Oh, and if I do, I'm guessing if I do 2, -1, 1, -1, 0, -1, 1 to -1, 2. Oh, so it actually just chops off from the ending. I see. -1 will just be the ending. If I make this 0, by the way, if I just set this to 0, would that be okay? Oh, I feel like we're so close. It's just an issue with first largest here. I think that's what's messing us up. From first smallest. So I tried to find a smaller one. Okay. Tried to find a larger one. And because there is no larger one, I can't actually find, I can't get the slice I need. Maybe we can also say here, like, if pre-order equals null, or pre-order dot length is equal to 0, return null. Because then can I just be a little more aggressive and just set this equal to that directly? If I kind of change first smallest to first largest, and here, what if we just do this? Don't know what this is here, because this would be like the nicest way of doing it, I think. But I think we might run into the same issue here. And this is with the same. Oh, we had it working. Now something's wrong. First smallest to first largest. Why was that working before? It was totally working before, right? Or again, is it because I'm not checking for? Yeah, no, I think we need to do the same check that we were doing before. Find index. -1 is return. Find last index, find first index. Oh, wrong thing. Okay, let's go back to the drawing board here. We have a 4 and a 2. Because I found a smaller one, that means that if I find a smaller one, then I definitely could call this function again, but there are sort of some caveats, like, okay, if I find a smaller one and larger one, take the slice. If I only find a smaller one, take the remainder. If I only find a larger one, take the remainder. Right? If I only find a smaller one, I can take the remainder. And if I only find a larger one take the remainder. Now it'd be nice to know, because it's not an or situation. It's whichever one is not -1. So it could be something like, if first smallest is not equal to -1 and first largest is not equal to -1, then here I think we can just do this, right? Because we can actually take a slice. Else if first smallest is equal to -1, if first smallest, that means I never found a smaller one. So preroot.left should be null, but preroot.right could be, yeah, preroot.right can just be the rest. Else here, never found a larger one, so this is null, and then here we can just take from the smallest onward. That could be a way of doing it. And there's probably a nicer way to refactor this. I'm looking at you, Steve. If Steve's watching, I'm looking at you. I know you got some nice refactoring tricks up your sleeve. So let me try running this again. Oh, and of course, I don't want to have that text in there. Let's run it. Doesn't like something here. First smallest, missed a parentheses. That's fine. It's all right. Oh, same thing, really. Man, that's so sad. We were doing well. We were doing well. If first smallest is not equal to -1 and first largest is not equal to -1. So let's see where we could be going wrong here. And where is it failing? Is it failing for this one? Is it failing for all of them? So it's failing for all of them. We had this working though. We really had it working. 857. Oh, I guess let's go through it on our own. This is going to be very good practice here. All right, we start with this. All right, so pre-root is equal to new tree node of pre-order at 0. So I'm going to create a new tree node here with 8. All right. First smallest, we want to find the index of pre-order of E, where E is less than pre-order. So that's going to be 1. Okay. And we want to do the first largest is where it's bigger, 2, 3, 4. That's 10. So that's index 4. So both first smallest is not equal to -1 and first largest is not equal to -1. So we're going to call this same thing again, but now with the slice of 1 to 4. So we're just going to take 517. Okay, so let me copy this. And I'm going to make an arrow down here. We're now going to call this with 517. All right, cool. Now we're starting again. First smallest or pre-root is new tree node at pre-order 0. All right, so we're going to create another one of these guys. I'm going to set it equal to 5. Nope, that's 6. So 5. Awesome. First smallest is 1. First largest is 2. So both of these are not equal to -1. So we'll go first smallest. We'll just go from first smallest to first largest. So the left is just going to be 1. So again, we call this left with just 1. All right, copy this, bring it down here, and we have a 1. And this thing is in the way. Okay, we get here, we have a new root of 1. Try to find the next smallest. All right, so if first smallest is not equal to -1 and first largest is not equal to -1. Oh, and I see else if first smallest. So I think here, probably what we should do is if both, maybe the first thing we should check is both. Oh, this is where I feel like now, if first smallest, yeah, I think maybe this is the case that I'm missing here. If first smallest equals -1, so if I didn't find anything, you also you know what we can do? I just realized something. We don't even need that. Here, maybe what I can do is say const pre-root. Here I can say if pre-order dot length is equal to 1. Maybe here we just say return new pre-node. Or even better, copy that same thing, put the if case down here. Let me just move this a little bit. We can just return pre-root. Return pre-root. So maybe that's where we messed up, because then here we just return pre-root. We go back here where the largest is 7, right? That's just index preorder.length is 1, so we just return 7 here. We're back at the 8. Now we go preorder.right. So we're now in here. We slice from 10 to 12. This could make it better. Let's run this. Okay. All right. We're making progress again. We're back. What was the other one? Was it 4.2? Let's try 4.2 and 4.0. Why not? Well, let's try 4.2. Can we see our submissions? 4.2. All right. So 4.2. 4.2 and 4.2. Are we going to get it, guys? I will go crazy if we get it. Like, that's crazy. All right, here we go. Oh my God, that's crazy. Oh my God, that makes me so happy. You don't know how happy that makes me. I don't even care about the time. I mean, we're able to pass it. I was, again, referring back to the person I was speaking to yesterday, Ivan, N3 Tutoring. It doesn't matter. It's good. It's great to get an optimal answer, but if you can make a pass, you're already like, that's half the battle, right? That's half the battle. Because sometimes people are struggling to even solve medium questions, like period. But we're over here doing the right thing. We're making it pass, and that makes me happy. Now, obviously, I think there's a lot of room here for improvement. I really wish it was easier for me to see where maybe I can make an improvement here. The thing is, it's the refactoring that sometimes gets me like confused. Now let me run this again and see if like, can it get better? 60%. All right, the find index. Yeah, the find index and then also the slicing is maybe what's killing me here. Do I even need to? I wonder, yeah, that'd be nice if we can just like, this is smaller, so go left. This is smaller, go left. This is greater. So then what we like pop here, but then that becomes this one's right. This one's greater. So then we pop here, that becomes this one's right. I wonder if we can do that. I mean, this is a good first effort, I think. If I can figure out a way to maybe, can I consolidate any of this? So preorder.left, let's see. Preorder.right is the one that I'm most curious about, because it's the same case whether first, I mean, like if both of them are, like whether both of them are, well, how do I say this? it's going to be the same. Yeah, first largest will always be the same as long as it's not -1, right? Yeah, first largest will always be the same as long as it's not -1. Maybe that's the first thing that we can do. I can say something like pre-root.right equals first largest equals -1. It's exactly what we had before. If it's equal to -1, it'll be null, else we'll just go ahead and call the same function like this. Right, so I think just with that, maybe I can remove all these. Now, is that going to give me the same? Okay, that's maybe slightly better. Now the left, first, this is where it's like completely different. It's going to be different for all the test cases. And maybe there's a better way. Maybe there's a better way of doing this. Like, what if I use like a truth table? If I had 0, 0, 0, 1, 1, 0, 1, 1. If both are null, then, well, both will just be null. Else I can use both. And here, either, like, if my largest, I guess the first one will be the largest, then I can just call largest. And if we find this one, I'll just use shortest. I know I'm using, this mostly makes sense to me. I know I'm using like terrible terminology here, but if they're both, and I guess in that case, that last case, if they're both, yeah, if I didn't find anything, that's handled by my base case here. I think it's, yeah, I think what I need to do is I need to figure out a way to like not slice and also not find indices, because this is an n operation. This is 2n plus another potential n. So I mean, we're doing linear time operations per. Might be a better way of doing it. Maybe I can say this is 8, and then if the next one is smaller, we can recurse and go left. This one's smaller, recurse and go left. This one's greater. So then what if we pop? Then we come back here. But now what do we do? Right? How do I know to pop again? Again, that's the part that it becomes tricky. 8, 5, 1, 7, 10. The slicing also is maybe not beneficial. But again, I mean, super stoked that we even made it this far. Again, I'm just happy. I'm so happy. This for me, I mean, 93.57. This to me shows like absolute improvement. Like if you're watching this and you're thinking, am I ever going to get better? You definitely will get better. I promise you. Let me see. Should we see discussions? Maybe just the titles. O of n solution. N log n and O of n. I really want to see it though. Find the left part and right part, then recursively construct the tree. This is binary search complexity. So let's see. BST from pre-order, return null, return root. So what are they doing? Give the function a bound. The maximum number will handle. The left recursion will take the elements smaller than node val. Right recursion will take the remaining elements smaller than bound. So wait, how does this work? BST from pre-order, BST from pre-order, where we have a bound. Wait, what? I have no idea how that's working. Mid to J and find the left and right part, then recursively construct the tree. Binary search. bisect, bisect, bisect. Solution 2, give the function a bound, the maximum number it will handle. But how does this AI++? New tree node AI++ I is 0. I don't understand how that part works. That's a little bit weird. But I think idea is simple. First item in pre-order list is the root to be considered. Okay. For the next item in the pre-order list, there are two cases to consider. If the value is less than the last item in the stack, it is the left child of last item. If the value is greater than the last item in the stack, pop it. The two appends can be combined. Is there anyone that uses root pre-node while I length is less than pre-order and pre-order I less than root.val, I plus or equals 1? Pre-order from 1 to root, okay. And self.preorder. So here they're just finding the index, I guess, with just using an index. They're just using their own index, it seems like, and then doing the same thing where we pass in sections of the array instead of using the slice function. Nice. So I mean, it looks like we're at least we're targeting some of the answers in the top like 4 or 5. So that's really nice. The first element of the array corresponds to the root. Then we find the split point corresponds. Okay. Auto split, find if, boom, 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 BST from first order. O of n times n in worst case, O of n log n in average case. For each node, we search for the split point, log n of average, n worst case. Instead, we can pass the parent value to the recursive function to generate the left subtree. We're searching for split point, so if IDX, let's see, new tree node pre-order IDX++. Instead, we can pass the parent value to the recursive function to generate the left subtree. IDX++. That's so weird. I'm not sure what that means, because pre-order is always going to be smaller, or actually we're always passing in pre-order here, and n, auto n equals new tree node n dot val and p underscore val. I should probably watch this on YouTube or something if I can find someone explaining this. It's funny because I'm trying to explain it my own way, but then explaining this is even beyond anything I figured out. So I'd like to see someone else's way of explaining it. Anyway, I think that'll wrap it up for us here today. Again, I thought we had a fantastic stream. We did 2 medium questions, which is awesome. 2 of them that I've never done before, right? Because we did minimum operations to make array equal. Yeah, 2 of these that I'm very happy with. I think that's really good, making a lot of progress. So that's going to put us at 306 questions. Yeah, that sounds good to me. So hope all you guys had a really fantastic time today. If you like LeetCode, you like problem solving, make sure to subscribe to me on YouTube, follow me on Twitch. I put all my content on YouTube. That's going to be the best place to see everything. And if you're interested in podcasts and you like LeetCode and competitive programming or anything related to that stuff, check out my podcast called Castware. Just like this, I uploaded my second video yesterday, had a ton of fun doing it, and it's also available on Spotify if that's your thing. All right, with all that being said, thank you all for joining today's stream. See you all tomorrow for a weekly roundup. Happy coding and happy October.